Have a Copernican view of the solar system, you will probably put the sun in the center of our solar system, the planets circling around it, and then we keep going out and expand, and we will follow the branch of our Milky Way all the way to the Milky Way galaxy in which we live, and the other galaxies all around. And then you can look further and further to the edge of the universe, the visible universe that we can experience today. Yeah, there it is. This red line down here, it appears like a red line, but actually it contains the information of the edge of the universe, the last information that we can perceive by light expanding from the cosmic microwave background to us. Physicists like to take a different view to this picture. They like to plot things in space and time, our coordinate system. So you will see time elapsing from the singularity, the 0 point in space and time when the universe was created, apparently with a big explosion, the Big Bang, and then very quickly developed into the size that we today know and experience and visibly experience. And after 13.8 billion years, we live at this epoch of the universe. Now, what do we know exactly about this history, the history of the universe? Well, we know that the universe is expanding. We know that in the early time, shortly after this explosion phase and this inflationary phase, which we will discuss in a moment, the institute, I lost for a moment, the universe, the entire universe. The universe was constituted by hot plasma. This hot plasma was just a soup of constituents that started to cool and cool over time. Now, one thing in advance, we always write down the time after the Big Bang. In this case, we are talking about less than a nanosecond after the Big Bang. And down here is also written the energy, which corresponds to the temperature at which we are looking back. So energy we express in GeV, giga electron volt, so 100 GeV, if you can calculate them with K. Boltzmann, the Boltzmann constant into temperature, they correspond to, I forgot, some 10 to the 12 Kelvin. So extremely hot temperatures. But you will see GeV, so energy is down here. Universe started to cool down, and actually somewhere exactly here at this transition stage, temperature 100 GeV, a very important transition took place. We call it the electroweak phase transition. This is just the point where electromagnetic and weak forces split, separated from each other, and actually via the so-called Higgs mechanism, elementary particles got their mass. Before we had a soup of constituents, and then particles acquired their mass. It's a phase transition, as you would expect from water becoming ice or vapor becoming ice. We don't know if it's first order or second order, but it's a transition into the particles that we know today. Then the universe keeps cooling and cooling, and we reach about 2 minutes after the Big Bang. We reach a temperature of equivalent to 10 MeV in energy. Now, 10 MeV, for those of you who remember a little bit of basic physics courses, is the energy, the binding energy of nuclei in the nucleus. This is the energy that gets the protons and the neutrons together in the nucleus of atoms. And indeed, neutrons and protons started to combine at this age and formed nuclei. They were charged, positively charged, electrons were still flying around wildly. The story keeps going, and we come 300,000 years after the Big Bang. And at that point, the temperature has cooled down to 1 electron volt ballpark. Electron volt is the binding energy of electrons in atoms. So at that point, the binding of electrons was possible, and atoms got formed. So 300,000 years after the Big Bang, all of a sudden something very important happened. By creating neutral atoms, the cosmos, the universe, made path free for photons to propagate. Before this time, photons were not able to propagate in the plasma. This is the cosmic microwave background era from which we get the earliest information from our universe. The story continues, and the universe expands, and temperature cools down all the way to the point that large scale structure are able to form. And there we are. We live today in a relatively empty universe, in a relatively cold universe, where many things have formed. Now, if we look at the universe today, and we look at the universe on very large scales, not at the scale of our sun system, but a scale maybe of 500 megaparsec, so 500 million times the distance to the Earth to the sun, we see that the universe is quite simple. It's actually quite symmetric. It looks something like this, where you wouldn't immediately recognize a structure. This is surprising. This makes us think, why is it so? And in order to understand why is it so, we have to go back to this phase after inflation, after the cosmic inflation, after the expansion of the universe at the beginning. And we have to look at what has happened here. This is a period of exponential growth. Now, at least after Corona, all of you should know what exponential growth means. It's a dramatic event. Things grow uncontrollably fast in a very short time. And indeed, the universe grew at that time, in an extremely short time, by 26 orders of magnitude. 10 to the 26 increase in size. That is the same if I would stand here and say, this is a bacterium, I have identified it, it's 10 micron in size, then I blink my eye for a second, and the bacterium is as big as the Milky Way. That is quite shocking if you think about it, but in the blink of an eye, a bacterium becomes the Milky Way. And the question is, does the Milky Way size bacterium still have some information of the bacteria that was at the beginning of this expansion? Is there any link between the two? And this is the key question. Whatever was back then, after the Big Bang, the structure that was there, during this cosmic inflation, got expanded by an incredible, stretched by an incredible size, and contributed to what we call the cosmic perturbation of the universe after inflation. If we assume that there was absolutely no structure back then at time zero or immediately after time zero, no perturbation would exist after inflation. That means no perturbation, no large-scale structure today. We would not be here today if the universe after inflation didn't have a structure. Why do we believe that there were perturbations, that there was a structure back then that got expanded, that got stretched by many, many orders of magnitude, of which the wavelength now is as large as the entire universe? Because we know that vacuum is not nothing. Vacuum is not emptiness. Absolute emptiness is a fluctuation of quantum states. And there we have to go back to quantum physics and understand what is the quantum origin vacuum, what is the structure that was back there, that is still in vacuum today, and that got stretched out and made the universe as it was after this expansion point. Okay, so just to recap, dramatic exponential expansion, a phase where we had plasma, no information, no photon information coming through the universe back then. Then all of a sudden, atoms formed and photons could propagate, and from there we get information. So basically, we receive today information from the cosmic microwave background, and we are blind to the period before this time. Nonetheless, let's look at this cosmic microwave background. You might have seen this sort of pictures. They made it to the press several times. This is an image of the entire universe, of our sky, observing the entire universe, taken from the satellite WMAP from the NASA. It shows temperature, the distribution of temperature in the universe. And you have to watch out, because here the large fluctuations known are already subtracted. The sun is gone. The center of the Milky Way is gone. Everything that we know is gone. So the temperature profile of known object is subtracted. And you see different colors. You see red to blue. So you ask yourself, well, what is the difference between red and blue? So first of all, you have to appreciate that the average temperature of the universe is 2.7 Kelvin, the lowest temperature that we can reach at the moment in our universe. In the lab, obviously, we can go much, much lower, luckily. The fluctuations, the red to blue point, are fluctuating at the level of millikelvin. So the fluctuations are extremely minor throughout the entire universe. Nonetheless, modeling these fluctuations, explaining the temperature profile of the universe, brought us a model that predicts the cosmological content of matter in the universe, and that is the model, the standard model of cosmology that predicts the content of matter and energy in the universe. And shockingly enough, we have learned, confirmed other experiments, that what we know of the universe, the matter and the forces that we know of the universe constitute only 5% of the total. 5% is known matter. A factor 5 more exists of matter, of particles with a mass interacting gravitationally, that we don't know and we cannot interact with. And an even larger factor, 70% of our entire universe, is something of even other nature. It's a type of energy which we call dark, because we have no idea. And if you want to embarrass me at the end of the talk, you can ask me, what do I know about dark energy? And many colleagues will follow me in being embarrassed and saying, we know very little. Let me tell you about things we know. We actually know this 5% quite well. Matter has been studied, has been categorized, has been understood. The standard model of elementary particle describes the matter content of the universe in its form of quarks, making up protons and neutrons, leptons, the forces that interact between them. And lately, since 2012, the Higgs particle, exactly, the so much wanted and searched for and finally found Higgs particle. We discovered it in two experiment, Atlas CMS at LHC, observing collision of protons, and we found this very special particle. The Higgs is not only the last of the standard model to have been found, is also different from all the other particles. First off, it's the only particle we have ever found, elementary particle, with spin 0. You know that elementary particles have this tendency to rotate around their own axis. They have a spin. Majority of fermions have spin half, 1/2. The forces, the bosons that interact, that transmit the forces between the fermions are of spin 1, and the Higgs is the only one with spin 0. We can ask ourselves why that is the case. So among the big open questions for fundamental physics these days is better understanding the Higgs particle itself, why it has a spin 0, what does it tell us? And the Higgs is also responsible for the vacuum. And the vacuum takes me back to this famous oscillation structure of the vacuum that I discussed before. There is another little thing that I have hidden from you, and that is, this is only half of the picture. All these particles, matter particle, come with an antiparticle, an antimatter particle. When we produce them in our collision, we turn energy into matter, and matter come always out in this experiment in equal amount as matter and antimatter, not to be confused with dark matter. They always come in pair, but we live here. And we are matter, we are not antimatter. We live in a universe that is made of matter. Why is it so? Why, at some point in the history of everything I told you, the universe decided to choose for matter and not antimatter? There must have been a little tiny difference, asymmetry in the amount of matter-antimatter at the origin, which we cannot find today, which we're looking for, we're trying to explain. Matter-antimatter asymmetry in the universe. Finally, obviously, we ask ourselves, what is dark matter? What is it made for? And how is it produced? And I will not touch upon the elephant in the room. What is the rest? What is dark energy? So I take you back 1 second to this picture that I showed you before. I told you the CMB, this image of the universe back then in time, told us all this. Can we ever get to know something from the earlier times? Can we go back even more in time and get closer to the Big Bang itself? Yes, we can. Yes, we can. Because since 2015, the LIGO collaboration has discovered gravitational waves. You must have heard the news in this sort of interferometer experiments that can measure black holes spiraling on each other, moving, accelerating mass in the universe and generating gravitational wave passing through the universe and inducing a chirp, this sound signal, if you wish, until the moment when these two black holes coalesce, merge into each other, and this process is stopped. We can measure gravitational wave. We have measured them with terrestrial interferometers in the wavelength of few hertz, few hundred hertz. We have also had the first astrophysical observation with nanograph in the nano hertz frequency range, and this has boosted what we call now the gravitational wave astronomy, the possibility to look at our cosmos, at our universe, and search for gravitational wave coming from different sources. And here, over the entire frequency range, new ideas popping up of more and more experiments that plan to look at smaller and smaller frequency, namely larger and larger wavelength structures, as large as the size of the entire universe in the end, if you go all the way down to the CMB mission. In the cluster, clearly we are involved in all this, both from the theoretical work and the experimental work in many of these experiments. And I just wanted to take this point here to make the bridge, to take you to our research. Now I gave you the big picture, and now I tell you what do we actually do. This is the beautiful picture of our cluster for 7 years' time. We will change it now in the renewal, if it comes on Thursday. We research on many different topics, and I will not bore you with the entire palette of our research. I will focus on 2 specific topics that I found particularly suited in this contest. I will talk about dark matter, and I will talk about gravitational wave. And I will focus particularly on experiments. I will not describe the theory developments, of which we have plenty. I will not describe the mathematical developments. And I will also, unfortunately, leave out a lot of the AI, so all the algorithm that we are developing to make use of the huge amount of data we get from all the experiments. I hope I made a fair selection to entertain you today. And obviously, if you want to know more, you can invite all my colleagues to come and describe all the other parts. Okay, let me get started. Dark matter. As I said, we don't really know what dark matter is. We know that it's there. We know the amount of dark matter in the universe from gravitational measurements, theoretically, it could be anything. It could be anything spanning from extremely low masses, much below the neutrino, the lightest elementary particle mass, to extremely large masses, even beyond the Planck scale. This is just a bit of a joke, but if I go to a more serious representation of candidates for dark matter, you find many theories. And we divide basically these candidates in two categories. Dark matter candidates that behave wave-like, so like a wave propagating through the universe, and candidate dark matter that are behaving as particles. And that depends on their energy. Somewhere at the electron volt, 1 electron volt is the divide. And though the cluster is active in many searches, so we're not believers, we're physicists, we search the different theories, we are active developing theories and probing theories. Today I decided to pick one specific example for you. I decided to talk about axions. For two reasons. First of all, because I'm directly involved and I find it particularly fascinating. And because axion-like particles down here in the wave-like domain answer not only the question of dark matter, but also another interesting riddle for particle physics. They provide the answer also to the problem of charge parity conservation in quantum chromodynamic. Or, differently formed, the missing electrodipole moment of the nucleons. So electric dipole moments, you know it from the molecule of water. You know that oxygen, negatively charged, and the two hydrogens in a molecule of water, positively charged, are displaced with an angle. And because of this angle, the positive and negative charge are actually displaced in space, and they constitute a dipole moment. This you all know. And now if you Google for neutron or proton, you will find this sort of representations. What is a proton or a neutron? Is a composite particle made of fundamental particles, quarks, and very often you find the 3 valence quarks depicted with some gluons exchange between them, and they are displayed as a triangle. Now, for the same logic, the up quark is positively charged, the down quarks are negatively charged. They would be displaced in this way, and the neutron is expected to have a dipole moment. Theory can tell you that the electric dipole moment of the neutron is proportional to this angle, the angle between the quarks. You can calculate that. That is a proportionality angle to amount of electric dipole moment. Experiments, though, tell us, after very careful measurement, that the electric dipole moment of the neutron is very, very close to 0. Physicists will never be able to tell you that it's exactly 0, but it's just below our sensitivity, and it's below 10 to the minus 26 in its units. That implies that the angle is smaller than 10 to the minus 10. I would call it 0. Therefore, the picture is wrong, and the quarks in a neutron or a proton are displayed like this. They should actually sit on a line and perfectly cancel each other charges. So this is odd. It's odd that Wikipedia is wrong, that the physicists are wrong in their textbooks, and it's odd that nature has chosen this specific angle. And this is what we call the CP conservation problem. How do we explain this problem? Well, physicists are always creative. They come up with crazy ideas. One idea is theta, this parameter, this angle, is not a universal constant. It's not like the speed of light, got given to be a certain number, but is a dynamic variable. That means at the beginning of the universe, it had some value, and then it oscillates over the time of the universe to this minimum, and the minimum happens to be 0 today. When you do such a thing, you have coherent oscillations of an angle. They generate new particles, and this is how the axion is generated by the oscillation of a field. So the axion comes out of this issue. Don't worry if you don't get the sense of it. It's just a theory. My task as an experimentalist is to prove if the theory is valid or wrong. So I ask, what should I measure? If all this is true, this theory is true, then the axion has a possibility to couple into two photons. That is, an axion is here between you and me, and it will fluctuate, and there is one probability, extremely small, that two photons will be produced. This will not happen in your lifetime, my lifetime, or the lifetime of many other generations, so we can't just wait for that. What we do, we provide one photon, one of these two photons externally. We give it to the process, and we wait for the second one to appear. Then we speed up a bit the process, or increase the probability for it to happen. And this is exactly how all these experiments are built, some of them in Hamburg, many more in the rest of the world. They differ in the type of source that we are looking for, but they are very similar in the detection principle. They just differ in wavelength. So the idea is that you look at a source. You decide what to look for. You can look for axion in the universe, in the halo of our galaxy. Then you build a haloscope. You can look at the sun and look for axions generated in the magnetic fields at the sun surface. And then you build helioscopes, or you can say, well, I don't trust any of this. I want to generate an axion in my lab. So you produce an axion, and then you convert it back and measure a photon. Those are the three types. And then what you do, basically, you just build a detector surrounded by a very large magnet, and you hope to see a photon. You close your experiment in the dark so that no photon will come to it that is unwanted, and you wait for a photon to appear. And indeed, this is the idea of the experiments we are setting up in Hamburg. We have partially prototyped. MEDMAX is one of them, dielectric disk materials inside a very strong magnetic field. Haloscope, we're waiting for an axion from the halo of the galaxy to convert on this dielectric disk, turn into photons, and we want to receive the signal of these photons in the gigahertz range. So this experiment works in the gigahertz range. YAXO, or the prototype baby YAXO, gigantic magnet pointing at the sun. The sun sends us axion, and they will convert inside this magnet and be detected on X-ray detector. So here we are talking about X-rays, keV range, looking for axions from the sun. And finally, light shining through the wall experiment type, experiments where I use a laser to generate an axion. I put my laser in a resonating cavity. I keep light in there inside a very strong magnetic field, and I put a wall after the cavity. And after this wall, I try to convert any possible axion that would pass through the wall completely undisturbed. I try to convert it back. And indeed, those are experiments that we have not only thought of, but we have built. So for instance, in the Hera tunnel, the former Hera tunnel, we had an accelerator. We still have an accelerator not functional under the Volkspark in Hamburg. We turn a session of that into a straight session. We have straightened up 12 and 12 dipole Hera magnets. We made them straight because we have to shoot with a laser at least into the first 12. This is our production cavity. The laser goes back and forth, and then it finds a wall somewhere here. Sorry, the ICA is just to show you the length of the thing. Obviously, there is no ICA in the experiment. That is clear. We put a wall, and in the second half, this is the regeneration cavity. We wait for a signal to appear, for a photon to materialize there in the magnetic field of the regeneration cavity. This is just some nice pictures to show you that the thing has actually taken place. With the tram, we have transported magnets after bending them straight. The dipole magnets of Hera were circular. We straightened them up in this very long straight session that was installed a few years back. This is the optical resonator cavity at the center, where basically the wall is placed and where the two branches are going off in the two directions. The other experiment I mentioned is MEDMEX, the sketch I showed you there. On the sketch, it looks small. In reality, the prototype, already the prototype to show that this technology is possible at all, it's a bit of a monstrous. We have just received this week the cryostat that will bring to 4 Kelvin our entire setup. So it's a very different thing than cryostat we use for qubits. This is a 3-meter long beast with 70 centimeter diameter. What we will put in there is a parabolic mirror shooting the beam, the photon beam into the antenna, the receiver, 20 to 100 gigahertz. If in the audience anybody has a solution how to read photons in the range of 100 gigahertz with a power of, sorry, this should not be a 20, obviously, but a 10 to the minus 23 watt. This is the sort of signal we expect to receive if if an axion converts into photons. So we are after 10 to the minus 23 watt of signal in 10 to 100 gigahertz. I would be welcoming anybody who gives me a solution for that. Just to give you an idea of the reach, this is the reach in mass of the axion. So as I said, we don't know where the mass of the axion is. It can be anything over many order of magnitude, and it will couple to photons with a coupling strength, with a probability, if you wish, that we also don't know. And we started the first 7 years of cluster. We have added some experiments up here. And in the second phase of the cluster, we will go down. We will increase our sensitivity to reach the theoretical predictions and possibly find an axiom. Okay, let me switch now to the last topic I wanted to touch upon, gravitational wave. I've shown you already the interferometer sketch. Is much more impressive when one sees the interferometer from above. This is the Livingston 4-kilometer long interferometer arms, one in this direction, one in that direction. So how do we detect gravitational wave to start with? Well, I told you gravitational waves are generated by masses, large, heavy masses being accelerated in space that produces a gravitational wave that propagates. If I put some sensing device, the gravitational wave passage will deform space and time, and I can measure the distance of these 2 points. And if I measure the distance also of these 2 points, I can measure the difference in the elongation. I can define something called the strain, which I will show in a couple of plots later. That's why I define it here. So the variation of the length divided by the length of the object I'm using, the baseline length of the interferometer. So the strain, if I have a 1 kilometer length long interferometer, I require a precision of 10 to the minus 18 meter. Precision of 10 to the minus 18 meter, just to bring it a bit in context for you, the atom core, the core of an atom, has a diameter of 10 to the minus 15 meter. So 3 orders of magnitude better. Okay? How do you reach that? Well, you have to get rid of any possible noise in your system. You have to reflect the laser light in these 2 interferometer arms on mirrors, which are then suspended and completely isolated from the background, from the surrounding. This is the signal I showed you already. This is the Nobel Prize signal. It's always beautiful to see it. This is the measurement of the LIGO interferometers. And this is compared to the model. And when you do data minus model, you see the residual fluctuations. And this residual fluctuation you can try to understand. There are some low frequency noise in this residual fluctuation. Those are related to the Brownian motion of the surface of the mirror. This is why you want to suspend this mirror with multi-layer suspension and maybe even cool them down to cryogenic temperatures. You have high frequency noise sources, which are mainly related to the photon counting, to photon statistics, Poissonian nature of shot noise in the system. And this you want to fight by reducing to sub-Poissonian the shot noise, or if you wish, using the squeezing possibility of quantum sensors, so the quantum correlation of the photon. That allows you to bring down the current limit. This is the limit I wanted to show you. Strain, we are at the 10 to the minus 23 almost. This was the number I showed you before. We are reaching the design level of LIGO. And for the future, we want to go even lower than that. Europe has committed to a project of building a 10-meter long telescope, Einstein telescope, increasing the length, so the L, and increasing the precision. Why do you want to do that? Well, if you increase by an order of magnitude, so a factor of 10, the sensitivity, you all of a sudden open up your view and can reach sources that are a factor 10 further away from us in distance, if you wish. So you see more of the universe, and that gives you, in 3 dimensions, a factor 1,000 more sources possible. But you can also start to see, especially if you go down in frequency here, you can start to see sources earlier and follow them while they spiral. And the earlier you see them, the earlier you can act and maybe trigger a net of other devices to look at the same sources. And one very quick project I would like to point you to, that is the wave seismic network, which is initiated by some colleagues listed here, is a project associated to the cluster, but really run as an independent network, providing measurement of seismic noise, seismic motion in the region of Bahrenfeld. So we have instrumented with optical fibers, part of the accelerator complex around DESY. And the idea is to collect a huge amount of different sensoric information to predict and to control seismic noise attenuation. And obviously there, like in all the other projects that I've mentioned so far, AI will play a major role in analyzing the large scale number of events and controlling them. If you want a blick in the future, a very fast look at the way ahead, and you're not happy with seismic noise, then you take your detector and you bring it into space, and then you're rid of all the seismic noise. And this is what is planned for the LISA gravitational wave detector complex with 3 spacecraft in orbit. The Pathfinder, this is the Pathfinder from NASA that was already sent in orbit in 2013, I believe, showed the possibility to use this method, and we're also involved in that. I might very quickly glance over the fact that once you're done with all this experiment, you still don't have the answer. You're still lacking the answer about the universe, and that's where we started from. So if you really want to understand the Big Bang and how it evolved to today's universe, you still need a theory that describes all what I try to describe here. A quantum gravity, a theory of quantum gravity, a theory that brings together general relativity, Einstein theory of relativity, and a quantum theory. Merge them together, and this is a very active part of the work of our cluster, which I haven't had the pleasure to discuss. String theory is a buzzword that clearly resonates in this frame. I stop here. I don't want to go into detail. I just want to close by telling you that basically this is what I discussed today with you. I took you from the smallest scale, the quantum scale, the elementary particle scale, 10 to the minus 18 meter of the universe, to the larger scale of the universe, the entire size of the universe as we see today, 10 to the 25 meter. I told you that there are extremely good theories that had extraordinary successes at the quantum level, standard model of particle physics, at the universe level, standard model of cosmology, but that we're missing the link between these two things. And this is exactly where we are working, where we hope to continue to work for 7 more years, we'll know on Thursday, to bring a link between mass and gravity. So stay tuned, follow Quantum Universe, see our faith and, and our research to come. Thanks a lot.